Hello everybody, welcome to CHM410 at the University of Toronto. My name's Andrew and I'm a TA for the course. We've put together some videos as a refresher or prep to get you thinking about why we use the various analytical techniques that we will employ in the labs for this class. In this video, we're going to be looking at the various calibration techniques or methods for quantification of a known analyte. Briefly, there are four calibration methods: external calibration, internal calibration, standard addition, and matrix matched calibration. These calibration techniques involve the preparation of a range of concentrations of the target analyte to create a calibration curve. In this lab, the analytes of interest have a large linear range with the UPLC triple quad. In this lab, you will explore linear ranges with very high and low concentrated standards. And once the curve is constructed, the sample is run and the concentration can be calculated through interpolation or extrapolation with standard addition, but we'll get to that. So, often one of the first challenges for any analytical chemist is what mode of quantification will be suitable, and thus, which calibration technique should be employed. There's often no clear answer, so the pros and cons of the various techniques should be considered before making your decision. And keep in mind, this may change after a couple trial runs. Here's some sample data from my own research with various quantification techniques used. For external calibration, a range of concentrations of the target analyte are prepared in clean, pure mobile phase, such as methanol or water, to create a calibration curve, as displayed here. You plot the concentration of your analyte on the x-axis and response on the y-axis. Depending on the concentrations used, you will want the calibration line to be as linear as possible. As you can see, pretty good. This has the benefit of easy sample preparation as well as minimal sample volume is needed. However, this will not account for matrix effects or differences in injection volume. For internal calibration, it is very similar to that of external. However, each calibration standard and sample are all spiked with the same concentration of the internal standard. And like before, when we graphed concentration of the target analyte versus response, here we will graph the concentration of the target analyte versus the ratio of the response of the analyte to the response of the internal standard. Now that may sound a little confusing, so let me show you what I mean. Here's some example raw data that was gathered from when I took the class. The analyte of interest, triphenylphosphate, or TPP, was quantified with its isotopically mass-labeled counterpart. We use this because aside from the extra neutrons, the compound will behave similarly as our target analyte, however, can be differentiated by the mass spec. Also, we know that it is not prevalent in the environment. Isotopically labeled compounds are ideal for internal standards. However, they aren't always available, and thus, you would have to choose a compound that is similarly structured and is retained in the LC column similarly. So, as I mentioned with the calibration curve, you've got your concentrations on the x-axis and then the ratio on the y-axis. Here, with the raw data, you can see that the internal standard peak area is more or less pretty constant. There's a couple variations, but this can be due to a variety of reasons. However, everything is normalized since we're taking the ratio of our analyte to the internal standard. And as I mentioned earlier, linear range is incredibly important for this type of analysis. And as a quick aside, when we speak about linear range, this becomes more important for Lab 3 when you're using the ESI source on the triple quad. And I'll kind of dive a little bit more into that. In this lab, you will look at a low calibration curve and a high calibration curve. This is because the ESI source on a triple quad has very small linear ranges, such that if you zoom out and analyze every single concentration from the LOD to very high concentrations, when the response levels out, the graph would look like an S shape, as you can kind of see here. Lower points go above the regression line and back below. This means that we need to have enough standard concentrations around the analyte's concentration to capture that small linear region. If you see here, the R-squared value is pretty good, 9934, if we used all points. But when we look at the low values, the regression line does not well characterize these points. Same is for the high points. As I mentioned earlier, some are above the line, now further below. So that is why in this lab, we will look at a low curve and a high curve to make sure our regression line characterizes the responses that we are seeing. So as I mentioned previously, graphing all the points together does not give us a great picture of the analytes and the responses that we will actually be getting, and thus calculating unknown concentrations will be an issue. So as you can see here, I've constructed a low calibration curve and a high calibration curve, both of which R-squareds are pretty good, and yet you can see the equation of these regression lines are quite different. This technique has the benefit of accounting for variations in injection volume. Since you're taking the ratio of the two compounds, it will remain constant with varying injection volumes, with minimal extra sample preparation. Also, this accounts for matrix effects, as both standard and internal standard will be equally interfered or amplified by the matrix, as well as minimal sample volume is needed. However, as mentioned, an ideal internal standard isn't always available. But if one is available, this is usually your best choice. For standard addition, we divide the sample up and add a range of concentrations of the target analyte to the samples themselves, and essentially make a calibration curve for each sample. As you can see here, our sample, and moving forward, we get the same concentration of it into each of our vials, let's say. And then we're adding increasing concentrations of our standard, and it will begin to look something like this. So here, I had 4 spikes, and I did a standard addition analysis for each of them, adding 2 parts per billion, 5, 10, and just over 16. And as I mentioned, you kind of get a calibration curve for each sample. Some things to keep in mind are that the concentration of the actual sample must remain constant for each standard addition and for your calculations to work. So, as I mentioned here, our calibration curves. Same as before, concentration on the x-axis, response on the y. However, this is just your pure sample, and then these are the samples with standard added to them. You will perform your linear regression and get your line of best fit, and then you will extrapolate and figure out what the x-intercept is. This can be done by setting y to 0 and solving for x, etc. But that x-intercept is the concentration of your sample. This is one of the most robust ways of quantifying the analyte of choice, aside from isotopically labeled internal standard, of course, because it accounts for all matrix effects, because each inject is the sample itself. However, it is definitely the most laborious. And finally, for matrix match calibration. This involves extracting quote-unquote clean matrix from the sample, from the same type of sample. For example, with my research, when I perform matrix matched calibration, I have clean blood or clean urine that I extract, the same as my samples. After extraction, you're left with your clean extract that has all the same sample matrix interference and co-extractables that your samples will have. You can use this as your solvent to perform the same steps as an external calibration curve with a range of concentrations prepared in your clean extract. Here, matrix effects can be accounted for. This is more robust than external calibration with only minimal increased labor. However, is not as thorough as a labeled internal standard or standard edition. I had to use this technique because a suitable internal standard was not available for my analytes, as well as I had very limited sample volume and was not able to divide that up and perform standard edition. Now, if you have any questions about any of these techniques, completely feel free to contact the lab demonstrator or your TA, and thanks for watching.